Okay, so I'm Michael Foord. I've been developing with Python since about 2002. I started as a hobbyist. I was lucky enough to get my first professional job with Python around about 2006, and I became a core developer in 2008. And as you can see, I've got up to various things in between, including creating unit test.mock, which is part of the standard library, and perhaps and hopefully many of you have used. And you should all follow me on Twitter. I'm absolutely hilarious, as I'm sure you can tell. Okay, so this talk is called How Python Took Over the World. And it's a hopefully fun and interesting look at a bit of my own personal journey with Python since 2002 and what's happened with Python since then, how Python has taken over the world, how we all are conquerors of the world through Python. And not only that, a look at some of the challenges that face Python in the months and the years to come, and indeed what we're doing about that as Python core developers and as a community. And the main reason I'm here is because, in my experience, Python people are beautiful people, and that's just as true here as it is anywhere else. But more importantly, the Python community is one of Python's superpowers and has a great deal to do in a very practical way with the rise and the growth and popularity of Python. And that's something that hopefully I will make clear as we go on. Okay, so like I said, I started learning Python as a hobby back in 2002. And this is what the python.org website looked like back in 2002. Not very similar to how it looked these days. You can see that Python 2.2 has just come out. So that was the new style classes, which have finally gone away in Python. When I say finally, I mean about a decade ago in Python 3, and we no longer have to explicitly inherit from objects. You'll also see up in the corner that Python 1.5.2 was still a thing. And I remember there were some versions of Red Hat that were stuck on Python 1.5.2 for years. So if you were writing Python web applications or Python CGIs, as I did, you had to make your code compatible with Python 1.5.2. You can also see there that Parrot was a thing. That was the underlying platform for Perl 6, which was going to be Perl's great saving. Back then, Perl was our great rival. Perl was the dynamic programming language, which for many people was how they fell in love with programming, was through Perl. There's so many advantages of having a dynamic type system, of which I'm sure you're familiar with. So Perl, not so widely used these days, but was very important in the history of computing and programming, and particularly enthusiast programming. And that's actually something that's of great importance, and that. So, 2006, I got my first programming job, and it was writing this, it was creating this. This is Resolver 1, now long defunct. This was a startup based in London, and we were writing a spreadsheet that was going to take over the world. As you can tell, that didn't happen. But the idea of it was that it was a spreadsheet that was programmable right from the ground up, the core object model. So the original intention that it was to have a dynamic language embedded into it, and the formulae that you put into the cells would then be compiled into code, and you could then add your own code at the beginning, so you could import functions and call them from in cells, or you could write code at the end, which had full access to the object model of the spreadsheet. It was beautiful, and you could do things like this. You had an interactive interpreter that was live into the environment of your spreadsheet. What happened was that they were targeting Windows and using the .NET framework, and IronPython wasn't even in 1.0 at the time. But we were doing full agile development, full test-driven development, and this was slightly before I arrived. The guys discovered that if you're doing test-driven development, dynamically typed languages are massively easier to test because you're not fighting the compiler. So they started to prototype the whole application in Python. It's not that uncommon a story, assuming that at some point they would hit some kind of wall with performance or something like that. They would rewrite the majority in C#, and we never hit that wall. The whole application was written in Python. So in order to look at the importance and the role of Python and how Python has changed and grown over this time and since those days, it's worth taking a step back and asking, well, what is a programming language? So what's the fundamental language that the computer speaks, the fundamental language of the CPU? Anyone want to give me an answer to that? It is a trick question. Anyone got any answers as to the fundamental language spoken by the computer? Well, the two wrong answers I'm looking for are either machine language or binary. Those are the two things that you might say are the fundamental language that a CPU speaks. And you'd be wrong. The fundamental language of a computer, the fundamental language that's spoken by the central processor is the electromagnetic dance across wires and etched silicon, choreographed by the beating of a quartz crystal at the heart of the machine. The computer knows nothing of your ones and zeros. It knows nothing of your objects. It knows nothing, depending on your definition of knowing. It's just a dance. Okay, so what are those ones and zeros? What is binary then? So binary, something we consider to be one of the lowest levels of what a computer does. Binary is a human abstraction. It's an abstraction that enables humans to reason about the behavior of the system. And it's a very low-level representation because it corresponds directly to the electromagnetic potential, doesn't it? The electric potential. A 1 is a positive potential, and a 0 is no potential. So it's it's an abstraction that maps very directly to what's going on in the machine. If we look at the 1001001, those correspond to the voltages on the pins of the data bus, I guess. But it's very hard to work with. It's very hard to understand. So one of the early great advances in programming was assembly language, was to start using symbols to represent these instructions. If you look at move ECX, EBX, that's an instruction that takes the contents of one register and puts it into another register. And it's a move instruction. And it's a lot easier to understand than the part of the diagram on the right. So this, on the left, assembly language, this is a better abstraction. It's closer to the way that humans think and reason. We're using symbols, understandable symbols, to represent the numbers. Another great advantage of doing this is that instead of specifying memory locations numerically and having to know the position that we've been loaded into memory, we can create labels, we can jump to labels, and we can let the assembler and the linker do the work for us in terms of calculating offsets and making jumps. So moving up a level of abstraction gives us this opportunity to make things simpler and easier. So fundamentally, programming languages are not for the computer. Programming languages are for people. And this explains a great deal of the success of Python and dynamically typed languages in general, in that they give us ways to reason about the behavior of the system that are much closer to the way we think naturally. And in fact, this is why I think, so I'll take a little step back. There are various programming paradigms, of which I'm sure you're aware of many of them: functional programming, procedural programming, object-oriented programming. And ever since I've been a programmer, people have been saying functional programming is the next best thing. Object-oriented programming is going to fade away. Functional programming, particularly with the way it deals with state, addresses a lot of the problems that object-oriented programming has. And people have been saying that for as long as I've been a programmer, and doubtless they will continue to say it. But my opinion is that object-oriented programming is a good fit for our minds, because it matches very well. It maps very well to the way we think about the real world. If you think about the world, if you think about objects, objects have behavior, and they have attributes. And what do we have in object-oriented programming? So the thing is, all programming is abstract. All programming is about abstractions. What's the concrete reality of a computer program? It exists maybe as electromagnetic patterns on a metal platter on a hard disk or in memory, but it has no real existence, does it? Programming is entirely abstract. This is why, partly why my consulting and contracting company is called Agile Abstractions. The goal of creating software is partly to create software that we can understand, that we can collaborate on, that we can maintain, And to do that, we have to have code that we can understand. And objects provide a way of building abstractions that help us to reason about our software. They say that a good programmer can hold about 10,000 lines of code in their head at one time. This sounds like an awful lot, but it seems about right. If you're buried in a project, you can know fairly intimately quite a lot of code. So if you're working on a system that's less than 10,000 lines of code and you're the only developer, it doesn't matter what structure you pick, because you'll probably be able to remember and work with the whole thing. But as soon as you stretch beyond the bounds of that, or other people come to work on the project, we need something else. We need another way of creating software. And objects and abstractions are one of the things that allow us to do that. We can take complexity and we can give it a label. We can create classes, and then we can inherit from them. We can have various other classes, and we don't need to know the details, all the lines of code for every single object, because the object itself, hopefully its name and its intention, tell us what it does, tell us the purpose. We can visualize, we can imagine the system in our heads because of the abstractions that we use. So Python, I think, sits at Python was originally created by Guido van Rossum, as I'm sure you're aware. And one of the things he did was, it was intended to be something that would sit between shell scripting and the lower level systems programming. And so the goal was that it should easily interact with system programming, with calling C code, but that should have a lot of the ease of use of shell programming. And that's a great position to sit, that layer of abstraction, the application layer of it. And I think this is a big part of Python's success. It provides great tools for building abstractions. So a question, how do you know whether you've got a good abstraction? Well, if you take a class, and if I ask you, what's the purpose of this class? If you can easily explain to me what its purpose is, there's a good chance it's a good abstraction. If you have to spend quite a long time telling me all the things it does, it's probably a bad abstraction. I think programmers use abstractions in two different ways. One is, I've created a lot of complexity and I can't understand it all. I can't hold it in my head. So I'm going to give it a name, and I'm never going to think about it again. And I'm just going to think about the name. It's the name, the label becomes something to cover up the mess you've made. Good abstractions, they don't hide complexity. They simplify and reveal complexity. This is how we can create and manage huge and complex systems through having good abstractions that enable us to reason about the software. I love this quote from Larry Wall, the creator of Perl. Computer languages differ not so much in what they make possible. If your programming language is Turing complete, you can write any other programming language in it. So fundamentally, it doesn't really matter what language we pick. But some languages make things easier than others. And there are other reasons to pick a programming language too. And we'll come to that with Python. So back in 2002, when I started, Python sits, this is the TOB Programming Community Index. It's a measure of how widely used programming languages are. It's of dubious quality, as all of these things are. However, it's relatively consistent in the way they measure. So it tells us something. And back in 2002, Python sits pretty much at the bottom of the chart. The only ones if you look at the key on the right, the only ones that it's not below are the ones that they haven't started tracking yet. And then sort of round about 2004, they changed the way they measure things, I think. And sort of round about 2008, 2009, 2010, just a little bit after I started using programming professionally, Python starts to get more successful and more popular. And you can see by 2019, it's one of the most widely used programming languages in the world. So Python really has taken over the world. One of the reasons for Python's great success is that it's able to go just about everywhere. And one of the places Python has gone very successfully is the data science world, the landscape for data science. Python has this very rich set of extensions I'm sure you're familiar with. I think Ronan used exactly the same slide in his. This is a great illustration of some of the massively popular libraries that are used in Python for machine learning, for data science, for all of these topics. And there's a bunch of ones that are not there. PyTorch is very big. And it's not just data science. Python is used for web development. It's used for system administration. It's used for genetics and bioinformatics. It's used for hardware testing and as a glue language. It's the standard extension language both in the GIS world, embedded in various programs, and in the animation world. You go to Disney Pixar, any of Python is embedded into Maya, I think. Python has had this huge reach by virtue of being this easy to use, easy to learn, general purpose programming language. And this has reached into some interesting places. This is a slide which is a snapshot of an article from a company called eFinancial Careers. And they really love Python. I don't know particularly why, but they've done various headlines about how Python has virtually replaced Excel in trading desks in the financial world. I don't think that's actually true, but it's a nice thing to read. And that they've done various articles how if you're looking to enter the financial world, you're doing a degree and you're not being taught Python, you're not being properly prepared for the world that you're entering. And that's a great place to be for us as Python developers, as Python becomes more and more ubiquitous. We're starting to teach it to 10 and 11-year-olds in the UK as part of the national curriculum. Well, not directly as part of the national curriculum. The national curriculum says a text-based programming language, and Python is tending to win there. So in about 20 years' time, there'll be a whole lot more competition from the UK for Python jobs. And this is another very interesting place that Python is going. And this is actually the project that I'm working on currently. This is a piece of software called Blueprint. I can't tell you very much more about it than what's on the slide and what I'm about to say, because I'm under NDA until we open source the project. But Blueprint is a piece of software for designing nuclear fusion reactors. The UK has 2 working fusion reactors in Culham, Oxfordshire, JET and MAST. The world record for the amount of power generated by a nuclear fusion reactor is held by JET, and it was about a decade ago. It was the last time they did a run with tritium. They have another one coming up this year. Back then, 2009, I think it was, they had a Q ratio of 0.65. That means for every watt they put in, they got 0.65 watts back out in power. So not generating power yet. In the run this year, with all the improvements they've made on the same JET fusion reactor, it's a tokamak-style reactor, MAST being a spherical tokamak, and being much smaller, they're hoping to get over 1.0. They're hoping to actually get a net power generation out of a nuclear fusion reactor. And Blueprint designs fusion reactors. It spits out wonderful diagrams and charts and full CAD designs of fusion reactors, and is hopefully going to be used in STEP, which is a UK project, and ITER and Demo, which are EU and worldwide projects for the design of those fusion reactors. And it's going to be entirely open source. And this leans very heavily on a lot of the heavyweight data science packages and data manipulation packages, NumPy, and so on. It's all possible because of the Python ecosystem. And obviously, the Python ecosystem is a huge reason to be using Python. And hopefully, I might be back again next year or the year after with the creator of Blueprint. I've been working with a scientist from Culham, and hopefully we'll be coming around and doing some talks and showing you Blueprint in action. I'm sure there's a whole bunch of stuff that I've forgotten along the way. But here we go. Okay, so something else that's happened in the same time space. There's been a couple of major developments, both in the programming world and in particular in Python. And one of those is the rise of DevOps. Now, you can see in 2012, very, very little. And by 2018, the interest in DevOps has grown a great deal. Now, I was very suspicious of DevOps when it first came out. I was convinced this was an excuse to get developers to do system administration work, and I didn't like system administration work. However, it turned out that some of the next steps in my career were to spend a few years working in Juju for Canonical, which is a deployment tool, that, a back-end agnostic deployment tool that can deploy systems to any cloud you want. And having spent a few years on that, I then went to work for Red Hat for a year, working on their test team for Ansible, Ansible Tower, another DevOps tool. And it's that system-level thinking. It's taking that thinking in terms of abstractions and being able to apply that not just to the components of your system, but to apply it to a whole system, to a distributed system, to be able to use the same patterns of thinking that we use when we are explaining our software. And don't forget that programming is essentially a two-way communication. You're explaining your software to the computer, and you're explaining your software to readers of the code. So those are the hallmarks of a good language. And in terms of something I omitted to say, in terms of building abstractions, using software to build abstractions, if the abstractions that you build in code, if they map to the way you think about the problem domain, so the way you think about your code matches the way you think about your problem domain, then there's going to be a lot less friction in terms of understanding and maintaining the code, because the same domain-specific knowledge that you use to understand your problem domain, you've actually encoded into your software. And then, of course, as software grows, as your software expands into more of the problem domain, you then find that you need to do this refactoring. You need to rethink your abstractions, because you're now solving a bigger problem. And I think this is something that is often omitted. I mean, how many of you can ever get your managers to sign off for budget and time for refactoring, to spend 3 weeks getting your software back to the point it is now, so that it's easier to work on in the future? It's a hard sell, isn't it? It's why we call it technical debt. And you need to include paying off your technical debt in your estimates for how long how long features will take to develop. Because managers are very rarely ever going to approve spending time producing nothing as they see it, paying off your technical debt. Anyway, so the rise of DevOps. This is a very real thing in the Python world. DevOps is massive. Python and AI is another one, massive rise. We have a data science track with several machine learning talks. This is something that is only going to increase and is going to change computing. It's a different way of doing programming. It's non-deterministic programming. It's programming where even the people who write the black boxes, the neural nets, don't really understand what they're doing. So AI is going to change software and writing software completely. And thankfully, Python is right at the forefront of that, largely because of where it sits, the layer of abstraction that it sits in. It makes it very easy to work, to have good abstractions, simple abstractions for very complex operations. So back to DevOps. This is a great book written by Moshe Zadka on DevOps. I highly recommend it. Very practical book. All the details of DevOps with Python. And reading it, one of the things that I really took away from it that sort of really struck me is something I was already kind of doing and that we're going to talk, I'll mention in passing later as well, this idea of disposable virtual environments. You should never use your system Python. You should never be using the main version of Python you have installed on your system. You should either be using something that has Python installed, has a system Python, or on a platform like Windows, you should install Python, and then you should never use it, except to create a new virtual environment. You can use Anaconda instead, particularly if you're living in the data science world. And then if you screw up your virtual environment, you blow it away. One of the things we learned that the good DevOps practices for any project is tightly track your dependencies, control your dependencies, have a requirements.txt file if you're using pip or the other tools have other mechanisms, but know what your dependencies are. Pin the versions. And then recreating a new virtual environment if you screw up, or moving on to a new computer and recreating your development environment is then a matter of minutes. So disposable virtual environments, is a great idea. This is another book that I'm recommending. It's just come out, hot off the press. I haven't actually read it yet, but it has some great interviews with prominent Python developers, so I have a bit of a vested interest in getting you to read this one. But the guys who wrote it, Noah Giff, Gorju, however you say his surname, Alfredo Deza, they're all prominent Python developers, seasoned and hardened, battle hardened. So this is, I'm sure this is a great book, and I do have an interview in it. Okay, right. So I've talked about how Python has become popular, some of the areas that it's pressing into. I haven't really talked so much about why. But let's move on to some of the challenges that face Python. Working with Juju for 3 years with Canonical was developing in Go. I've been told off for saying this in keynote talks before, but I'm going to say it anyway. My impression of Go was that ultimately it's a tedious language to work with. However, it has some great ideas. Interfaces and structural typing are fantastic, and there are obviously advantages to working with statically typed languages, the tool chain. However, we have some of that in Python now with abstract base classes, with type annotations. Those together, I think, make a very powerful new way of modeling behavior in Python, something else I could talk about at great length. However, one of the things that Go has that it gets very right, that is great, is the model for concurrency they used. We've had a couple of people talking about concurrency. How long have I got? I've probably got enough time to talk about the GIL, the Global Interpreter Lock, which particularly Andrew mentioned in his first in the first talk, and he was singing the praises of the Global Interpreter Lock. So let's talk a little bit about concurrency, running things simultaneously. So as Andrew mentioned, of course, async programming is not true concurrency and is cheating, because you don't actually run things at the same time. And in Python, in pure Python code, you can't, because we have the Global Interpreter Lock. That means that only one thread of Python code runs at the same time. Threads in Python are true system threads. They're not green threads. The underlying a Python thread is a real system thread. So if you have code in a C extension, or even something like regular expressions, which call into the Python standard library, an extension is free to call release GIL and to run truly in parallel with other Python code or other C code in the same process. And when it needs to communicate back or work with any objects back in Python land, it calls acquire GIL and waits for its turn. But we still have this problem that only one thread is running at a time in Python code. And as Andrew said, back in the day when there was only one CPU, that didn't matter anyway, because you actually only had one thread actually running at a time anyway. So if you split your code up to run into multiple threads, it would run slower, because only one thread is actually on the CPU at a time. And there's a cost for that context switching. And the advantage of the GIL is that it means that a lot of the Python internals and for C extensions, they don't need to be thread safe, because only one thread is running at a time. And that for years, that was a great advantage, and it was a good trade-off. Now that multi-core is predominant, it's not such a good trade-off. Very few popular languages have a global interpreter lock, and there are many, many reasons why it would be good to be able to run multiple threads of Python code simultaneously. Go has a great model based on CSP and the actor model for making threaded code safer and easier to work with. So Larry Hastings, one of the Python core developers, said, right, let's have a look at the Python global interpreter lock. Let's see if we can get rid of it and add the appropriate locking in all the right places so that we can have multiple threads running in parallel. And he's done that, and it slows single-threaded code down a great deal, an unacceptable amount. And the major reason for this is because of Python's reference counting. Again, something that Andrew touched on is that every time you get a reference to an object, if you're a function and you're passed an object, you take a reference, you get a reference to the object. So you increment the reference count field in the C struct that underlies every Python object in CPython. And incrementing a number is fundamentally thread unsafe. And it's not too hard to explain why. We have a reference count. We have 3 things have references to this object. So the reference count is 3. We have the code x plus equals 1, so it's an integer we're taking a reference to, and we have 2 threads attempting to do this simultaneously. Now, x plus equals 1 in Python is essentially identical to read the value of x, and when I say essentially, maybe even down to the bytecode actually identical. Take the value of x, add 1 to it, and assign the new value back. So we've got our 2 threads of Python code. We've got running simultaneously. They both read x round about the same time, and there's a reference count of 3. They both add 1 to it, get the answer 4, and write that back. So the reference count is now 4. But we've just taken 2 references to the object. And when both of those decrement, we're going to end up with a reference count that's 1 lower than it should be. So this is the fundamental problem with multi-threading in Python. We need to lock around every operation. Anything that takes a reference to an object needs to be protected by a lock. And it simply results in an unacceptable slowdown. Now, thankfully, because Python is big, we have alternative implementations of Python. We have an implementation of Python in C#. IronPython, we have an implementation of Python in Python, or PyPy. And both of those have experimented with writing C APIs that are compatible with CPython, that work with existing extensions, but yet run on a platform that doesn't use reference counting for garbage collection under the hood and are able to be compatible. So we've run the experiments in the wild. We know it can be done. We know that you can have a language that doesn't use reference counting internally and yet remains compatible with existing code that does reference counting. So we have a path. Removing the GIL is already done. That code exists. If we can get rid of reference counting, which is only a massive job, then the path to true free threading in Python is there. There are, however, other attempts, and one you might have heard of that I particularly like because it's particularly close naturally to the actor model, to the CSP model. And this is by Eric Snow and others, multiple interpreters. Python has long had sub-interpreters. You've been able to run multiple interpreters in one process used by ModPython, the Apache extension, for example. But it has lots of problems and issues, and it didn't have a Python-level API. One of the things that IronPython had was the IronPython engine was a C# object. One of the greater points of IronPython is it makes it very easy to work with .NET objects natively. So you could create and instantiate an IronPython engine from within Python code in a thread and have it executed. There was no global interpreter lock in IronPython, and have it executing. You could have multiple IronPython engines in a process executing concurrently. And this is the model with a Python API for doing it. This is the model that Eric has taken for multiple interpreters in the standard lib, essentially. And this is very interesting. One of the difficulties with that is that when you pass objects between interpreters, we have to be able to guarantee that we don't do things like access the reference count simultaneously from different threads. So there's a real challenge to getting this working. There are various stages, and the work is actually coming on. This is going to land. It's happening. This is one of the ways we're addressing concurrency within core Python. Okay, so something that I really believe is that the community is Python's superpower. When I first started using Python in 2002, when I first became a professional developer, 2006, you saw that Python was pretty low down in the charts. What that meant was that most of the people using it weren't getting paid for it in their day job. They used it because they loved it, because they were passionate about Python, because they used it at every opportunity, even if they weren't getting paid for it. And this meant that the people who were using Python were fairly close-knit and really cared about the language. And I think this is something that has carried Python in great stead, because Python is not just a language. Python is a whole shared and common understanding about idioms, practices, patterns, tooling, tool chains that has evolved and come out of not just the core developers, but the whole community of the users of Python. However, the community is not perfect. This is one of my favorite counterexamples of community at work. This is the @decorator symbol. This was Python 2.4. One of the reasons I really loved going to work on Resolver 1 was because IronPython started at Python 2.4, and at the time, all of my projects were maintaining compatibility with Python 2.2. So as soon as I started working on IronPython, I got to use decorators. I got to use loads of the good stuff that came into Python 2.4. But decorators were massively controversial. The @ syntax, essentially no one except Guido thought it was a good idea. And he did it anyway, and it was a great idea. Okay, so the community is not always right. However, there are times when they are right. Who likes arguing over style issues? I actually ask this, and I get people saying yes. Who likes arguing? I'll fight you all. I don't really like arguing. Black by Wuka Schwanger, Python core developer, is a tool for ending Python style discussions. You get to choose any style you want, so long as it's black. Modeled on GoFMut, a great invention from the Go community, built into Go, is a reformatting tool, another way that we have this cross-pollination between languages. There's been a lot of that over the years, which has been really interesting to use. And unless you're a great fan of style arguments, I recommend using black. And another aspect of the Python community is that we do have people that it's worth listening to, who really know what they're talking about. The article on the right is by Brett Cannon. He's explaining the right and the best way to create virtual environments per project. Have a .env in your .gitignore per project, and have an active virtual environment per project created thusly. And Brett Cannon, he's one of the Python core developers. I would look up the article rather than try. Python-m VM means Python-m means VM means run the VM standard library module as a tool, and create me a new virtual environment called .vm. And this is an isolated virtual environment into which you can install all your dependencies and mess around with as much as you want, and then blow it away if you screw it up and start again. This is Hinek Slavak. Another, not a Python, probably is a Python core developer by now. And again, very in touch with Python packaging issues, worth following on Twitter, worth reading his blog. This is an article about where we store the metadata about a project. Where do you store the version number? In the code? Also in your packaging? Python 3.8 introduces a new metadata API that gives us one place to put the metadata and one place to read it from. And he explains the migration process as well. So Hinek is someone definitely worth listening to. And there are lots of people like this in the Python community. Christian, Marietta. As a community, we have evolved and settled on tools that solve a lot of problems. If you always use a virtual environment, there are a whole class of problems you just won't have. Screwing up your system Python will never happen to you. And we have a whole bunch of idioms and practices like that, evolved and proclaimed, if you like, by our community leaders. Something else that's happened very recently in the Python world, and very significant. This is Guido and some of the other core developers at the Python Core Sprint 2019. Python no longer has a benevolent dictator for life. And it has a steering council, and Guido is not on the steering council anymore. So Python governance has changed massively in the last few years. And really, we're into new territory with that, as to how that's going to work out. And the relationship between the steering committee, the core developers, and things like our Python enhancement proposals, PEPs, how those relationships and processes work out is still in the process of evolving and changing. But Guido is still around and still involved. The core developers are getting better at recruiting new developers and communication. The future of Python looks really bright. And I have 45 seconds on the clock left. I'd forgotten this was the next slide. So, I hope that was interesting, and thank you very much.